Good morning, friends. We'll start radiographic testing today. Radiographic testing. RT is a powerful volumetric inspection method which employs ionizing radiation as its probing medium. So it is a volumetric, the things which have volume, it can probe, it can understand. As an advantage of RT over the methods is that many RT techniques provide a permanent record of test result. So volume like shrinkage, porosity, piping, a very big crack, so everything is volume, then it is okay. Atomic structure, but if it is planar like lamination and all, RT cannot. Atom is that core comprises of its core comprises of protons with essentially all atoms mass is concentrated, electrons with negative charge, negligible mass, orbit the nucleus in specific paths. A substance made up of only one type of atom is called an element. Atomic number and mass. The atomic number Z number refers to number of protons. The atomic mass number is the total number of protons and neutrons. Cobalt 60 versus 60 cobalt, or iridium 192 versus 192. So these isotopes are stable and thus not useful for NDT, whereas others are unstable and consequently radioactive. These isotopes are called radioisotopes. Ionizing radiation commonly used in RT including X-rays, gamma rays, and neutron radiography. X-rays and gamma rays are part of electromagnetic spectrum and have wavelengths shorter, meaning a higher frequency than ultraviolet light. Wavelength is reciprocal of frequency. Electron cells. Electrons exhibit characteristic of both waves and particles. So there are several electron cells, K cell, L cell, M cell. So 2 plus 8 plus 8, like that it will go. Then 18, so KLM and OP, it can go further. Okay. The inner cell K electron have less energy than L and M cell electron. Those in the outermost cell are called valence electrons. These electrons are important for electrical conductivity of a material. When a K cell electron is ejected from its location by an incident X-ray or gamma photons, that space will be backfilled by a higher energy L or M cell electron. Excess energy of the outer cell electron is discarded as a secondary, that is fluorescent X-ray photon with a characteristic wavelength. For example, K alpha for L to K transition, K beta for M to K transition. Characteristic X-ray wavelengths are unique, although transition between two elements may directly overlap. Radiation source. X-ray tubes, isotopes, nuclear reactors. The X-ray tube holds a cathode, source of electron, and anode, target for the electrons under high vacuum. Electrons are accelerated towards the positively charged anode, and those electrons that are deflected and slowed as they interacted with the nuclei of a higher density metallic target material emit X-ray photons in the form of beam slung or breaking radiation. Beam-slung radiation is a continuous spectrum of X-ray with sharp peaks corresponding to secondary X-ray wavelengths of the tube target material. The shortest wavelength X-ray emitted by the X-ray tube is governed by the maximum kinetic energy imparted to the electron. Kinetic energy is controlled by the electron oscillating voltage potential, often measured in thousands of electron volts (keV) between the cathode and anode. Radiation flux emitted by an X-ray tube varies with current, measured in milliamperes, while the voltage controls the penetrating power, which is to say the quality and flux of the beam. So voltage in, increase the quality and flux of the beam and penetrating power. As the voltage is increased, X-rays of shorter wavelength with more penetrating power are produced, as well as more X-rays of the same wavelength as at lower voltage, increasing quality of the beam. Increasing Z number of the X-ray tube target also increases quality of the photons and the quality of the beam. On the other hand, filtering of beam decreases flux while increasing quality. So filtering is discarding the soft X-rays, observing. Many radioactive decay processes lead to formation of daughter elements that are different elements from the parent radioisotope. So these are characteristic X-rays, beam slung emission with characteristic X-ray peaks from tungsten target, 160 kilovolt X-ray tube fitted with 1 mm aluminum filter. And spectra are viewed as energy versus intensity, wavelength versus intensity. Low energy photons are filtered out. And the highest energy emitted is governed by voltage potential keV. Half-life of a radioisotope. For radioisotopes, the number of photons produced is controlled by number of unstable atoms present, activity, and their half-life, which is time required for half of the radioactive material to decay or transmute into daughter elements. 5.27 years for cobalt-60 emits photons with energy 1.33 MeV and 1.17 MeV. 73.8 days for iridium-192 emits photons with energies 0.6 MeV, 0.47 MeV, and 0.31 MeV. Source activity is measured in becquerels. 1 becquerel equal to 1 decay event per second. Unlikely X-ray sources, gamma ray sources cannot be turned up. Inverse square law. This law states that radiation energy I and dose rate is inversely proportional to square of the distance d from the source. I1 by I2 equal to d2 by d1 square whole square. That is linear and mass attenuation. Two values are useful, especially when considering health and safety aspect of usage and storage of radiation source. The half value layer HBl and the 10th value layer TBl. HBl is the thickness of a particular material required to reduce the intensity of radiation to a particular energy half of its original level. Likewise, the TBl is the thickness required for a 10th fold decrease. HBl of a cobalt-60 source is 12.5 mm of lead, while less intense gamma rays from an iridium-192 source require only 4.8 mm lead. roughly equivalent to 660 keV X-ray source. To decrease the dose rate by half the kVl of a cobalt-60 source. At a cobalt-60 source, it is approximately 41 mm of lead, 10th value layer, TVL. One TVL is about 3.33 something HPL. Check it. The radiograph is a static image record produced by passage of penetrating radiation in a straight line through the object and onto the detection medium. Most detectors convert photon flux into variation of grayscale on an image. For example, high flux shown as dark spots projected onto film or light spots projected onto image intensifier. The ionizing radiation strikes the sensitive silver-based grains of the film. A physical change occurs in the grain that makes it reactive with the alkaline chemical developer. This chemical reduction reaction converts the grain to black metallic silver. Unexposed grains are not reduced to opaque black. And when viewed with backlighting, the film produces an image of test object. Although film has been popular for decades, alternatives to film have quickly been gaining acceptance. Photoemulsifiable phosphorimaging plates are somewhat flexible, reusable, and store the radiation-induced charge within the crystal structure of the material as metastable discontinuity color centers. That is, electrons are holes, and holes, as the term photoemulsifiable suggests, the latent image held by the plate is recovered later by raster scanning with a laser, which simulates a spontaneous emission of light. Localized color center phosphorescence, the intensity of which is proportional to the number of radiation photons observed, is recorded to produce a digital radiographic image. Viewing in real time. Real-time radiographic viewing may use fluorescent screens, which are viewed directly through a radiation blocking port, as they emit light caused by radiation excitation. However, such detectors offer no ability to retain data for later analysis. So with radiation, you can see fluorescent with the fluorescent screens. It will directly come as a visible light, so you can see the picture, but there is no record. The photon encounters scintillation layer. For example, gadolinium oxysulfide, cesium iodide, which converts ionizing radiation into visible light. The visible light photon is detected by array of photodiodes. The photodiodes converts the visible light photon into an accumulated electrical charge in the amorphous semiconductor layer. Finally, a computer reads the electrical charge pattern to produce radiographic image. High flat band detective quantum efficiency (DQE) leads to rapid image acquisition and higher frame rates. So digital radiography, computed radiography all came in 2011. Image definition and resolution. Images produced by radiographic testing may be larger than the physical size of the test object by altering the distance between the test object and detector. Increased specimen to detector distance with larger spot size will lead to poor edge definition. Several image quality indicators styles are available, and these are used to demonstrate that radiographic testing procedure has met the required quality levels. IQIs including hole in plaque, wired step wedge with holes, and duplex wire pair type help to assess the three factors: image sharpness, image contrast, and image noise. Demonstrating the relative magnification abilities of the three different X-ray tube focal spot size as captured with the image intensifier. Computed tomography. Tomography is the most powerful RT technique for obtaining three-dimensional radiographic data. Digital data is collected at a multitude of projection angles, often by rotating the sample, and at a multitude of levels along the height of the sample. The digital data is compiled by computer into virtual cross-section slices called tomograph. The three-dimensional representation of the sample interior and exterior. Acquiring data from multiple angles facilitates calculation the relative linear attenuation coefficients for each volume pixel element. Computed tomography can provide quantitative information about the density, composition, dimension of the featured element. Backscatter imaging. Backscatter X-ray allows for single-sided evaluation technique. There are three common X-ray backscatter techniques: elastic scattering for low energy diffraction, compound scattering for detection of dense material such as opaque drugs or high explosives. X-ray fluorescence used to analyze surface chemistry. X-ray fluorescence is quite common in the industry and is often referred to as positive material identification (PMI). PMI directs X-rays of or gamma rays towards the spectrum, and this radiation induce characteristic X-rays to be produced within the sample's material. Incident photons interact with the electron orbiting atom and sample material. When electrons are ejected from their orbit, the sample material emits radiation energy. This emitted energy has characteristic wavelengths that vary with the elements being interrogated. This energy is detected by test unit. The spontaneous production of fluorescent characteristic of X-rays is therefore called X-ray fluorescence (XRF). They are mathematically processing the detect energy. The unit provides its interpretation of chemistry of the sample. Advantages and limitations. Radiographic testing is a powerful volumetric examination method that provides image results that are easily archived. Images may be static shadow images, or results may be viewed in real time. RT can inspect parts of essentially any shape, size, and material type for internal or external discontinuities. Radiographic testing presents significant health and safety concerns because of potential exposure to significant level of ionizing radiation. In addition, the initial capital investment is significant, Most RT techniques require access to at least two sides of the specimen because transmitted radiation must be detected. RT is sensitive to changes in density or thickness. Therefore, cracks and delamination type discontinuities are only detectable when imaged nearly parallel. Neutron radiography. The sources of neutron. Nuclear reactor, research facilities, particular accelerators, or cyclotrons tubes projecting a neutron beam into a related target. DT tube and radioisotopes. The best powerful and popular option. Neutrons useful in entity called thermal neutrons, which have collided enough times with a moderator material for graphite or water until their kinetic energy or velocity is equal to the thermal energy of the moderator nuclei. Similar to X-ray and gamma ray source, neutron sources may employ a collimator, which decreases the apparent size of the radiation source and increase the image sharpness as well as acquisition time. The material do not attenuate thermal neutrons at the same rate as they do in X-ray and gamma ray photons. Because of neutrons, unlike X-rays, may quickly be attenuated by water and carbon and can penetrate very thick sections like high Z elements such as lead. High degree of contrast between elements in the objects is possible, such as inspecting radioactive material. Direct transfer technique. Direct neutron radiographic testing exposes the sample and the film to the neutron radiation beam. Although the film is exposed by radiation emitted by conversion screen, for example, made of gadolinium, the conversion screen, which held in intimate contact with the film, absorbs the neutron and then decays by emission to beta particle and gamma rays, which ionize the radiation sensitive grains of the film. The exposed film is then processed in the typical manner as we are in radiographic room, dark room. Other detector options are also possible, including neutron sensitivity photoemulsifiable phosphor plates, package imaging using boron converter and cellulose nitrate film, and neutron sensitive image intensifiers. Indirect technique uses conversion foil screens. Indirect neutron radiographic testing useful for radioactive samples. Doesn't present the film to radiation beam. Instead of conversion foil screen, for example, dysprosium or indium is irradiated by neutron beam and thus activated. No other type of radiation will be activate the screen. Therefore, it is sensitive only to the neutron passing through the sample. Later, the film and the screens are introduced and the film is exposed. The screen radioisotope decays. The latent image is thus transferred from screen to the film. Because of indirect imaging relies on radioactive decay events rather than beam transmission, it must slower than the direct imaging. For instance, 8 hours versus 5 minutes. Okay, we'll stop here.